Hi everyone, welcome to the last session of today. Thank you for laughing at my joke, but that wasn't actually a joke. So the first talk is presenting functors, and I believe Gabriel's going to give it.
Thank you very much.
Profunctors.
So hi everyone, thanks for attending this talk. I'm really happy to be here. The organizers of this meeting have been very smart, because thanks to the talks that you've already seen, I'll be able to go a little bit faster at the beginning. So the general context of this is computational category theory. So that means that we're going to be interested in describing categories in some syntactic way and operating on them, right? The good news is that there are canonical ways of doing this for categories, category presentations that have already been mentioned today, for functors between them, and also for pre-sheaves and co-pre-sheaves. So all of this is the standard. But when you go to profunctors, there hasn't been like such a detailed study of what the right way to present them is. And well, a profunctor between categories C and D can be thought of, for instance, as either a functor from C up times D to Z, or as a functor from C up to the co-pre-sheaf category on D. But the thing that we're going to explore here is that although these are equivalent at the semantic level, they're not equivalent at the syntactic level if we take the natural syntactic representation of these two things. And this is the subtle thing that we're interested in. So first of all, I'll give some motivation for the context in which we're interested in, which is categorical database theory, right? And well, this is the same idea that Michael already mentioned. And I really like this phrase of David, that if you follow this idea, then every theorem about small categories becomes a theorem of databases. Like, I think that's kind of like the original idea, or at least the way I take it. And by the way, this is not the last version, let's say, of the data model. Like, there are some additional niceties that we can work with, and that will be the content of Emilio's talk next. But we'll stick to this relatively simpler model because the subtlety we're interested in is already here. So this is the part that I'll go a little bit faster. So a category representation consists of objects, generating arrows and equations between parallel paths there. And our beloved example, I'm not going to do Stargate, I'm sorry. I'm going to stick with this and unrelated stuff. But yeah, so this is just suggestively labeled things, right? Like, this is just objects or sorts and generating arrows or function symbols in logical jargon. And we have some equations. Would say that manager works in after manager, right? We're writing from left to right, and the dot is concatenation of paths is equal to just works in, and well, we'll talk about that later, maybe, if it's really important. And yeah, there you can see what I'm talking about. And every category representation will give a category which we denote like that, and which we'll call the semantics of C, or the interpretation of C, where the morphisms are paths quotiented by a relation that we'll call provable equality, right? Because we're really working with equational logic here. And the equations generate, well, anything you can prove from those equations will be provably equal. So here's an example worked out where you can see how the morphisms, well, we can group them by the length of the path that they came from. And the only really important thing that I wanted to mention here is that this is infinite, right? In this case, after you reach this employee object, you can start looping your manager, and you'll never get the same morphism as before. So that's why we use presentations. They give you a way of working with infinite stuff in a finite way. And the difference with, well, Michael's talk, there's plenty of differences with Michael's talk, but we will be focusing on the syntactic aspect, like we're going to go there. I'm going to explain a little bit more in detail what a morphism of category representations is, because I will omit the precise definitions of all other morphisms in the context because we don't have time. But essentially what you're doing is assigning objects to objects and generating arrows to paths in the target presentation. And in this case, we are looking at an endomorphism of our beloved example. which is sending each object to itself. It's sending the arrows manager and workstin to themselves too. And the only interesting thing is it's sending the secretary arrow, which I also like because you could read it as section because you're requiring that it's a section. It's mapped to, well, sec followed by manager. And for this to be a well-defined morphism, you have to require that every equation in the domain category representation is respected, which means that when you map the two paths, well, you have to check that those are co-equal. And well, you can just check that in this case. I won't go through the example. And in this way, we obtain a category representation, a category of category representations, which has its natural or obvious semantics functor into the category of small categories. This is also something that I might be able to skip or like go much faster. This is an example, Coqui sheaf, and this is really the point where you really understand why this would be a database scheme, right? Until now, this were just suggestively named things. Now you can see that you can populate these objects with some actual elements, and you can visualize this with tables in the way that Michael explained, and that already gives you a notion of database in which every object has a table and every column is either like the elements of the set or the well, where that element is being mapped to by the functions in the Coqui sheaf. And yeah, these are like foreign keys in the sense that they refer to tables, to objects, to rows in other tables. But now we want to go to presentations for these things too, because we also want to be able to work with infinite Coqui sheafs. And now I will start using instance and Coqui sheaf interchangeably because it's a bit more of a mouthful to be saying Coqui sheaf every time. But those are the same thing, right? Okay. So we define instance presentations. This would be like actions of monoids or groups, but it's a similar idea if you've ever seen presentations for those, but maybe they are not so common. So we're going to give some generators which are labeled by an object of the category representations and some equations. This is the simplest possible example with one generator in object employee and no equations, and then you can figure out what the table is. This is just essentially applying all possible map. You generate new elements by declaring those elements to be the images that you get from starting from this unique generator. And since there are no equations, we're not identifying anything with anything else. So these are all distinct. Here is the formal definition of what I just showed, or the one that we will use. It's not necessarily the most obvious one to anyone, but it will be useful for us later to do it this way. Which is that we take our original category representation and we extend it with a unique object asterisk. And we add arrows coming out of it and equations that must involve those arrows. For instance, here, this was kind of like very simple, no equations, but we can add the equation that E.manager equals E, and that is validating what I said because it's an equation between paths that involve this arrow. And the morphism of these things, well, it should assign these new generators or arrows that I added to something else. They should assign them to paths in an appropriate way. This is also could be said to be a category presentation morphism, which is required to be like the identity, to fix the asterisk and be the identity. That's another way of saying it. Now, we should also talk about manipulating data because that's part of what a data model.
Previous slide. So these are no longer like natural transformations between the instances.
These are, yes, I mean, these are presentations of natural transformations. Yes, that's a very good point to clarify what we're doing. But yeah, I mean, when you take this, the semantics of this is natural transformations.
This coincides with like the normal definition.
Yeah, it coincides. We're trying to reproduce everything in syntactic terms, not do something new in that sense. And now we get to the part where I talk about querying or transforming these database instances. And I didn't include a slide on the data migration functors that Michael showed, because here we're going to talk about something completely different, or well, not completely different, which is using profunctors. So we'll get to that, but we first start with just instances, right? So what we will do is to consider a finitely presented instance as a conjunctive query, and use the idea that conjunctive queries are things that can be represented by mapping out of some model, right? So we're going to map out of an instance, and that will be our query, right? And in this example, the first example, well, I don't know. It's presenting a representable, right? Like Ioneta says that representables are the free co-sheaves on one generator, quite literally. So the result of querying with this will just give me the set of all employees, if we're interpreting it that way. The second one will give you like a filter on that. It will give you the set of employees who are their own managers. And this is good. This is intuitive. We can program with this, but it's not expressive enough, for example, in comparison to the data migration functors, because it really gives you a set as an answer, and you might want something more structured. So you might want to produce a new instance. And we can do that following the same idea of conjunctive queries, but now having like more than one at the same time. And that's a way of seeing profunctors. So we will think of the profunctor as a functor from C up to the co-sheaf category and D, and define its evaluation functor using this construction that is kind of like appears all around, but it's you can see how this contains a previous situation when the domain is the terminal category, right? Now you're just, this C co-sheaf, right? Once you have plugged in a D co-sheaf, given some objects in C, well, gives you the ways of mapping PC to J. And an important thing for us is composing. Yeah, composing queries is important because you want to be able to manipulate in different ways your queries before having the data come in, right? Before actually looking at it. And this is all fine because profunctor composition, which, well, we're using this notation in this order, and I just put here for reference the Cohen formula one can use for composition. Well, this works in the sense that you can compose the evaluations, and it's the same as the evaluation of the composite. And this would be a great moment for an example, but I need to introduce some stuff, and then it will be easier. So our first attempt at a profunctor presentation will be just generalizing the instance presentations that I showed. So now we will have a category presentation that extends simultaneously to categories C and D with some profunctor symbols that have a domain in C and a codomain in D, plus some equations between parallel cross paths, where a cross path means that it has to go through some of these symbols at some point. And this notion turns out to be equivalent to C op times D instance presentations. I can't really define that because I'd have to say what op and times means for presentations, but you can. And you can define morphisms to obtain a category which enjoys this semantics functor also straightforwardly. Now, there's a problem with this kind of presentation. And for that, let me say this definition. So if we have two finite category presentations and a profunctor between the presented categories, if it admits a finite profunctor presentation, a finite uncurried profunctor presentation, then we say it's finitely uncurried presentable. And the problem is this theorem. It says that the class of finitely uncurried presentable profunctors is not closed under composition. And the proof of this is through a minimal counterexample. So I'll go through it quickly. In this example, there are three category presentations which have one object each and no equations at all. And we have two uncurried profunctor presentations which have one generator, one profunctor symbol each, and no equations at all. I think I didn't mention the F. I skipped that. There's one morphism or generating arrow in only one of the category presentations. And then you just look at the semantics of all this. And so you find out that this is presenting a profunctor with an infinite number of elements. These are all distinct. The same happens with Q. I'm going to go through this quickly. And when you look at the composite of these profunctors, it also gives you an infinite number of elements. Now, this profunctor has as domain a category with no morphisms or no arrow generating arrows, and this one either. So it's not possible to present that with a finite number of symbols. Now, the solution in this case will be to remember that we have this equivalence and go to the other way of thinking about this. So we will take this idea and kind of unflatten it into two layers. So now we'll think of one part of this data as being an instance presentation, and then this part is another instance presentation, and we will have morphisms of instance presentations between them. These morphisms, well, of course, they will have to satisfy the equations in the domain in a suitable sense, and we call this curried profunctor presentations. By the way, I'm skipping through many of the formal definitions, but that's just in the interest of time. It's not that they're particularly if I had an hour, I would just give them. But I think it's clear enough this way. Again, you can define morphisms between these, and you obtain a category of curried profunctor presentations between C and D, and its semantics functor. Now, the way this solves the problem is by giving an explicit syntactic composite construction, which we denote with this circled asterisk. And this is obtained by following like an algorithm that is known as subquery on nesting or the unfolding, and it's already sketched in the categorical database literature here. The important thing to know about this, firstly, is that it preserves finiteness, right? If we start with finite things, we will keep the finiteness. So we prove that this is a functorial construction. Well, we'll put more things in terms of like, well, these are there's a double category here and so on, but that didn't get into the talk. And there is a natural isomorphism telling us that this is correct with respect to the semantics of profunctor composition, which is fundamental, because otherwise I wouldn't even be talking about this construction. And as a corollary, the class of finitely curried presentable profunctors is closed under composition, which is great for implementation. And now I would like to give an example, which is kind of like more complicated. Well, it has a new category presentation, which is like a duplication of this one, except for one morphism that is like going. I think I might not have time to really go through it. I have already like 20 minutes. But the idea is that you can define a curried profunctor presentation here. So you do that by defining instance presentations corresponding to each of the objects here. I've actually included the generators in this pictorial form, even though this is not uncurried. This is defined in this way. And then you have to define some morphisms here. And then to showcase how you compose, I said, okay, let's go to the instance presentation that I showed you before, but now we see it as a profunctor. And then we can compose. And the idea, more or less, is that we look at pairs of composable generators and we tensor them. So we obtain a new generator that we write like this with a tensor notation. And then we have to take all the equations around there that could be relevant, and we obtain equations of the right type, let's say, by tensoring them on the left and on the right with the generators, with all possible choices. Yeah, I think I don't have time to go through this in more detail. But it's once you define how to extend the tensor operation to paths in general and not just generators, this is really straightforward. And the results, and this is also something that I wanted to emphasize, is that you get, since what you get has a domain which is presenting the terminal category, this is an instance too. And as an instance, we can think of it as a conjunctive query. And what it's saying, it's like a migration. Well, it is a migration of the original query, the original conjunctive query that was on this schema to this new schema. The original conjunctive query said, give me all the employees who are their own managers. And now we're saying, give me all the pairs of an administrator and a teacher. I didn't explain it, but such that the manager of the teacher is the administrator and the administrator is its own manager, their own. So it kind of makes sense intuitively. And the last thing that I want to talk about is a little bit of what failed in the uncurried case and how we could fix that by adding some conditions on what an uncurried presentation should satisfy. So this might be a point that is, well, it's really a very interesting point. I hope I can get it across. So the point is that we want to guarantee the existence of a finite set of generators for a composite. And the syntactic construction that I showed is one way of achieving that. And what we did was pair generators from two profunctors P and Q into new generators. Now, why did this work? It worked because the second profunctor presentation has these morphisms Q of F for every generating arrow in the intermediate category. And these morphisms always tell you how you can in a sense, look at a cross path that doesn't start with a Q, with a profunctor symbol from Q, and move to the right. Like apply, in a sense, this F to Q and obtain a new path that starts with a profunctor symbol. You need that because otherwise, when you write this little thing, this is now an atom, right? You can't have things in the middle between the P and the Q. You need that. So when we look at an uncurried presentation, we don't have the morphisms like that, but we could still require that every cross path can be rewritten to start with a profunctor symbol. And there's a simpler way of stating this, but that's it here. And in that case, we say that the uncurried profunctor presentation is non-generative. It turns out that we need another condition because we also want the number of equations to be finite. Otherwise, it would just finitely generate it. And to do this, we look at this little definition, which is that starting from an uncurried presentation, we can look at instances inside. So we pick one of the objects in the domain and forget about everything else in the domain. And this is kind of a restriction. We call it that way. And suppose that for every pair of paths that start in this C that we chose, if these are provably equal in the larger context, then they are already provably equal inside this instance, using all the equations here. And if that happens, we say that, well, that has to happen for all choices of C. And in that case, we say this is conservative in the sense of like conservative extensions. And we said that P is curriable if it's both conservative and non-generative. And now this will give us an equivalence, right? But to state it, we can look at a transformation in the opposite direction, which is like the flattening of a curried into an uncurried presentation. This determines a functor, which restricts to the finite and also preserves the semantics, which are the two things that we're interested in. And now we have to identify sort of like the target that we want to look at, which we will define like this, curriable from C to D, to be a non-false subcategory of the uncurried presentations, where we look at the curriable presentations, so that ones that satisfy these two conditions, plus a little technical condition in the morphisms that says that all cross paths are sent to paths that start with a profunctor symbol. And then when we co-restrict, we restrict the codomain of this functor, then it's an equivalence of categories. So we have captured the essential composability or finite composability of this of the curried presentations using uncurried presentations. And here is like an ending remark that there are different ways to state this. So we could drop this technical condition and take curriable to be a full subcategory, which will be nicer conceptually. But that leads us to a bi-equivalence. So we have to weaken a little bit the notion of equivalence. But I didn't talk about the like two-dimensional part of this, which is simply the provable equalities. Like when these two syntactic objects behave in the same way semantically, well, those constitute the two cells, and in that way, many of these could be considered by categories or something setoid enriched. That would be another way of thinking of them. And then we have a bioequivalence between them, and that's maybe nicer. It depends, right? You could want the more concrete thing, it's thinking in terms of implementations, or the more abstract thing if you like it. And yeah, that's it.
Okay. So we have a few minutes for questions. Yeah.
Dynamic schema is beautiful to do. It seems like
Yes, I mean, I actually originally the first slide said category representation, but it's a matter of just like going between the syntax and the semantics. You can define like that data model completely without any syntax, and for the audience here, that would be acceptable. It's actually, I don't know if that answered.
Any more? Yeah.
So you can take the thing further and say that a profunctor corresponds to a co-continuous function. Appreciate categories as well. And if you view things that way, then you're between three co-conclusions. So there may also be a way of talking about presentations and that animal that's,
You think that would, I mean, yes, I guess you could try to come up with a syntactic notion that would capture co-continuous functors between co-appreciative categories. But I feel like, I mean, if there was a different way of doing that, then it's.
it was just an idea. I wasn't saying.
Yeah. I mean, I haven't thought about that, but.
you have the composite of profunctor presentations as a finite presentation. Have you thought about doing the ensemble profunctor, the one given by the end, that's dual to the profunctor composition?
Oh, yeah, no, I don't think we have. I don't know if you know.
So it would be the
But,
other data migration.
Yes, there are some like dualities like that lead to kind of like similar but unexpected things. But there is something. Well, Emilio will mention that aside, like we don't just have the evaluation, the profunctor, we also have the co-evaluation of the profunctor, which behaves in an interesting way. We won't get into that though, but this is different because you're changing the notion of composition. That might be interesting to look at. Yeah, thank you.
Okay, one last question.
You mentioned that you need to set a finite number of transitions that are allowable. On the slide where you were talking about the limitations of the query and query process, you need to pick a finite number of what does it?
Yes, like if you want the composite to be finite, you somehow extract the finite number of generators, which are like generating arrows.
Yeah, is that a manual process, like up to the implementer?
No, like in the context, this is like for this construction, it's just take all symbols from the first profunctor and all the symbols from the second, and whenever they're composed of it or like they match in the appropriate sense, you just create a new profunctor symbol translated by them. But what I was trying to say in that sentence was that if you wanted to come up with some other way of composing presentations, even if it was by hand, you would have to do it somehow.
Okay, thank you again.